Okay, so everybody, thank you so much for joining this GRMS online webinar series, part one, Introduction to HyperSpy. So for those who are not familiar with GLMS, we're Great Lakes Microscopy Society. We are a local affiliated society under the Microscopy Society of America, MSA, and also a regional affiliated society under Microanalysis Society, MAS. And as a local microscopy society, we're serving mostly Great Lakes area, including Michigan and the northwest part of Ohio. But we welcome all the enthusiastic microscopists, students, researchers to join our events. So in the next couple of months, we are planning to host a series of webinars with a focus on HyperSpy and its ecosystem for microscopic data analysis and the processing. And for this intro session, we have invited Dr. Carter Francis, who is one of the authors of HyperSpy and also the key maintainers of the HyperSpy and the other related packages. So a brief introduction for Carter. Dr. Carter Francis is a research and development scientist working with direct electron to develop software and hardware for material science research. He did his PhD at UW Medicine under Professor Paul Weiss, who is now the president of MSA. And his work was on characterization of disordered materials using 4D STEM and in situ 4D STEM. And in addition to working for Direct Electron, Carter is also a member of the HyperSpy Steering Council and is the lead developer for the 4D STEM analysis package, Pixum. I'm sure in the future webinar series, we will go through the every details in each packages, including the Pixum. So in today's introduction, Carter will give us a good like big picture overview of the HyperSpy, followed by some live coding and the demo session. So I'm not gonna waste time, so I'll give screen to Carter. So Carter, please.
Yeah, I can share my screen. So I will. Oh, you have to send a request for screen sharing. Thank you for the introduction.
Oh,
A little
and
bit.
sorry for if you have any questions, please leave the questions to the chat. So we'll make sure we will at the end of the webinar we'll answer all the questions as well.
Yeah, exactly. So we'll start to, if you have any questions, I might even try and stop a little, stop in between and check the chat just to see if some people have questions, and I can answer them kind of in as I'm going along. So just a short overview, just because a lot of the times what we really care about is how to actually use the package. But so my name is Carter Francis. I work now for Direct Electron. We make detectors for doing we make detectors for anything from like cryo-EM to material science, yields, all of that sort of stuff. But today I'm going to be talking about this open source package, HyperSpy. And so HyperSpy itself is a package that was started by Francisco de la Peña in 2007, 2008. Originally, it was called EELS Lab. So like a bunch of the original publications for HyperSpy will be filed under that. And really the idea when Francisco was, originally doing this was he really just didn't want to be using kind of proprietary software to do his data analysis. And so he started writing code in Python to do it. So it was originally Python 2. This is right around the time where Python was really starting to become, something. For example, I think matplotlib was first started in 2004, and then SciPy was kind of started around 2007. So you kind of get the idea of that it was really at the ground level of what, when Python was started. And as it's grown, eventually it turned from just specifically being EELS and EDS analysis to doing, doing stuff like looking at HADF images, to doing 4D STEM, to Kikuchi diffraction. So there's kind of a large number of different packages that kind of all fall under this same umbrella. What's really cool about HyperSpy is the fact that it's, there's contributions from over 100 different organizations all around the world. And there's never been any funding source. So HyperSpy really hasn't ever had some central funding source. It's not tied to any one country, any one organization, any company. It's really just it's made by a bunch of scientists just like you, and we're all driven by volunteer work and contributions. And we've seen pretty steady growth. So what we've seen is, it's pretty actively downloaded. We get about 10,000 downloads a month, maybe slightly more these days, because I think these numbers are slightly old. Over 1,000 different citations, 70 plus different contributors to the base HyperSpy organization, used by 180 different packages and GitHub. And over 500 stars, and you can kind of see we've got this pretty linear growth, which is quite nice to see. Is that more people are really interested in open source solutions. So from that, the next question is, oh my gosh, I have way too many tabs open, so we'll just close that out and. Okay, so where do you get help? So if you type in hyperspy.org, you'll go to this landing page. This is the landing page for our entire organization. You can see here, we just received a nice award from the French government for open source science. This was something we were really excited about. You can read the kind of news here. And then if you go down here, you can see latest news. There's a tutorial right here. And then these will be all of kind of different ways to get started. So if you want to get started, usually this right here, this will bring us to your documentation, and you can look through and see different examples, stuff like that as well. When you have questions, what you can do is you can go to the actual GitHub account, the actual GitHub page. And there's this discussions page right here. And so what happens here usually is we've got a bunch of different, types of discussions. So you might say, you might go here and create new discussion, and then have a Q&A, and then just, create a question. You can say like, how do I load my data? And if you submit a question like this, then basically the answer will get posted by a bunch of different people who've worked on the package, and you can start to, you can get information that way. So this is kind of like, I'd start first with the documentation, see if there's an example, then go here and then add a new discussion. Okay. So then there's the question of like, what is HyperSpy? And so I actually have an image that I sent to myself, but didn't get into the presentation. And so let me just download that and pull this up. So this right here is kind of the structure of HyperSpy. And so you can see what HyperSpy is HyperSpy depends on a lot of different libraries. In this case, it depends on this library Dask, SciPy, Matplotlib, NumPy. We have these two libraries over here, ZAR and HDF5. These are kind of for ways in which data can be saved. And then under the hood, we've got different packages. So this Rosetta SciIO package, this is basically a package for reading and writing data. HyperSpy is kind of the central package. This is a package for kind of visualization of multidimensional data. And then there's a bunch of these extension packages. So there's this Particle Spy. This is for doing analysis on particles and kind of like live in situ stuff. So how something grows over time. XSpy, this is the EELS EDS analysis package that was split out of HyperSpy. LumiSpy, this is cathode luminescence. AtomMap, this is for doing atomic resolution, finding the center of a atom position. HoloSpy, this is electron holography. And then we have PixM and KikuchiPy for doing 4D STEM, and this is Kikuchi diffraction. And then there's also these two other libraries, Oryx and DiffSims. These are kind of under the PixM umbrella. Oryx is doing if you've used MTech before, it's kind of the Python equivalent of that. So looking at rotations and crystal orientations. And then DiffSims, this is like a very simple kinematic diffraction simulation package. If you're trying to do more complex simulations, then I'd recommend something like AbTem. But this is kind of a quick and dirty way to get some kinematic diffraction information. So now we're gonna just jump almost immediately into getting started. So let's see here. So if you go to GitHub, what you'll see is that if you look at a repository, you can see I have way too many different repositories, but there is this so this GitHub project basically this repository will be kind of what we're working through. In this case, we'll just start with this getting started page. And what you can do here is, if you're on a Mac, you should be able to do something like this. If you're on a Windows computer, you can open up, I think, PowerShell, and you can clone it this way. I guess. Let's see right here. So what this cloning is doing, this is using this package called Git, and it'll basically copy all of the contents of this folder to your local device. You can also do this and do this code, and then download this zip, and then uncompress this zip file. The nice thing about doing this here is, we can do. So we can just define a remote. We'll go through that maybe next time. But what this should do is, in this case, we have my file, and now this is basically been downloaded into my root directory. So we have this webinar and just getting started. And here we have some notebooks. There's so the next step would be to start up a Jupyter notebook. And so if you haven't already, there are lots of instructions on this web page. So let me I think I can put this in the chat, right? There we go, chat. How do I do it in Windows? Yeah, so to do it in Windows, maybe the easiest thing to do would just be to download this zip file, and then we can access this. Yeah, so is there any concrete advantage to using any HyperSpy instead of the single sub packages that it relies on? So it's kind of like the way that this works is like everything builds on each other. And so, for example, like PixM builds on all of the fundamentals of yeah, so the same command should work on PowerShell. So that basically everything builds on the previous package. So for example, everything that works in HyperSpy will also work in Pixem, and they kind of, it's just an extra extension to the HyperSpy package. And so the reason why everything is kind of split out like this is just because, you know, if you only do 40STEM, you might not need the EELS tools. If you only do, you know, you probably don't need also the cathode luminescence tools. And so there's lots of this kind of, so the nice thing is that you can kind of pick and choose what you download and install. But it does, and it also like really helps from a maintenance standpoint. So for example, there's, you know, I can help maintain the Pixem project with, because I know a lot about 40STEM, but a lot of the, you know, higher level HyperSpy specific things, you know, those things for a lot of even people developing tools, a lot of the HyperSpy stuff is you know, a different level of its, you know, it's difficult to understand how the plotting sometimes works. And so the idea there is that we can kind of develop more and more of these extension packages. Okay, so yeah, if you haven't already downloaded you know, HyperSpy and everything, I would recommend going through this getting started you know, at some point later. If you haven't already downloaded HyperSpy or you don't feel comfortable, what you can also do is click this launch binder link right here. And what this will do is this will build a binder instance. And so you can, it's basically the same thing, but now it's not running locally on your computer. It's running remotely on some server somewhere that, you know, somebody's donated time on. And so it will take a little while for it to kind of launch. But once it's launched, it will be a, you know, you can basically follow along and do the same things. The only thing you can't do is you can't make the plots pop out of the page. So then you could just, you know, get started here. So lots of different options there. For everybody else, if you, let's start here. What you can do is you can go into, on a Mac, you'll just say Jupyter Lab. On a Windows computer, you'll open up and it will say launch HyperSpy bundle prompt if you've done it through HyperSpy. If you've downloaded the bundle, you know, there's multiple different ways in which you can launch this Jupyter Lab, and maybe we can talk about more specifics if people have questions at the end. So if I type in this Jupyter Lab, at least in my computer, what it will do is it will launch this Jupyter Lab instance. As you can see, all of the different projects, and then basically this will be my file system right here. So it'll start at the top. You should be able to find the GMLS 2025 data analysis webinar. And so now you can see this. You can see I have way more Python environments than probably anybody else here will. And what you can do is you can just open up this unfilled one. Hopefully this environment's working. Okay, perfect. So now what you should be able to do is open up this Python it's IPython notebook. So you can see here we've gone GMLS data analysis, getting started, and we've started with this unfilled one. And so we're going to kind of go along that. We have about another hour, right?
Yes.
Okay, perfect. Yeah. So we'll try and get through this notebook in the hour. But you know, if we have to, we can switch to this completed one, and then that will kind of work slightly faster. So I'm gonna cheat a little bit and put the completed one up next so I don't get don't get lost. Uh, okay. Let's see if we have. Cool. So now, if you've gotten this open, you can kind of see this summary. Getting started requires basically HyperSpy 2 or above. And then you can see all the different people who have edited this over the years and how it's kind of grown and evolved. So, so if you haven't used Jupyter before, we'll start with maybe some tips. So if you see this right here is, you see how right now, if I click in here, now this window is blue. This means that you're basically editing this cell right here. If you click outside and you see this this blue bar over here, now you're in this command mode. And so then you can do a lot of extra commands. So for example, if I push A, that will create a cell above it. If you push B, that will create a cell below it. If you push D twice, it will delete a cell. If you click M, this will change it to what's called a markdown cell. You can also see up here that it will go back. And here, and the nice thing about a markdown cell is that you can write things like, this is a, you can create a header. I'm working on this data set. And then you can see when you click, so when you kind of execute this cell using Shift plus Enter or Shift plus Return, it'll render it nicely. And so this is nice for, if you want to, make something nice like this. You can actually double click these and kind of see how all of this is created in this notebook, how we, include things like links and whatnot. But then once you click Shift Enter, then you will exit that and you'll kind of jump. So the first thing what we're going to do is we're going to import HyperSpy. So import HyperSpy.api as HS. And what this will do is now you've imported HyperSpy. If you just look at it, you can type in HS and then do Shift Enter again, and you'll see the package. If you put dot and then so then let's kind of move on and let's see actually more about the HyperSpy object. So for example, we can use this question mark, HS question mark, and this will show us everything that's included within this package. So you can see we've got this function, we've got this hs.load, preferences, set log level, signals, plots, data, all of these different things. So for example, I can go hs.load, and if I start typing L and then press tab, you can see it auto completes. So auto completes to load, and that's really helpful for kind of navigating the entire project. The other thing we can do is we can use the directory function. So if we use dir hs, that will kind of give us a little bit more of a reduced visualization of different packages. So basically what I can say is hs dot any of these. So hs dot data, hs dot version, which will give us the version of it, hs dot load, any of these things are all shown up there. So let's talk a little bit more about the structure. Let's see what we've got. So for example, let's look at hs.data and some atomic resolution image. So here we've got this atomic resolution image, and this is going to be a function. We've got these two curly back brackets, parentheses, and so this is a function, and we're going to call it. And so if we call it, what it's going to do is it's going to run this function and then return an object. In this case, what we have is a signal 2D, so it's an image, and it's only got these two. It's basically a 512 by 512 image. So if we actually look at image and we set image is equal to, actually we should be more atomic resolution. So if we do that, then we can see now this is our atomic resolution image. And this image has properties that if we push period and then push tab, we can kind of see it has a bunch of different functions, a bunch of different instances, a bunch of these these are all different attributes of this object, and whatnot. We had a question earlier about the HyperSpy extensions. So basically, the way that HyperSpy works is that every data set is basically a signal. And so, for example, if we do hs.signals, we can see these are different types of signals. We have a base signal, we have a signal 1D, signal 2D. So this would be like a spectra. This would be an image. And then we have a complex signal. So these would be like if you have a 1D and then if you have an imaginary and a real component. So one for both of these. And the way that HyperSpy works is that you can think of, let's say that you have a atomic resolution image. So this is just an image. You would have two signal dimensions. Let's say you have a 40 stem data set. Now you might have, you might have something that is two navigation dimensions and two signal dimensions. And we'll talk maybe some more about how that looks. So we had this idea of like extensions. So there's this function in HyperSpy called print known signal types. And what this will do is this will go through and it will list all of the known signal types. And so HyperSpy.signals knows 1, 2, 3, 4, 5, 6 different signal types. But now we have a bunch of other different classes which kind of extend these signals. You can see some come from PixM, LumiSpy, XSpy, HuchiPy, and these are all things that are related to those individual packages. And so you can see right now this atomic resolution image is just a basic signal 2D. But let's say that we wanted to, we could try and set it as an electron. So this is a good learning point right here. So you can see I messed up a little bit. So if you see here and read here, this is red. It's a syntax error, and so this didn't run. And so if you read here, you can see, okay, it's an incomplete input, and what it didn't like is the fact that my parenthesis was the wrong way. So if I do this set signal type as electron diffraction, now this is an electron diffraction 2D instead of a signal 2D. It's not because it's still an atomic resolution image, but what ends up happening is there's lots of different methods that are associated with the electron diffraction image, like centering the zero beam, doing a polar unwrapping, things like that, all live within this electron diffraction class, which extends the signal 2D. So you basically get all of the original functions that are in the signal 2D class, but now you get a bunch of extra things that are extended by this PixM package. Okay, let's see if we got any questions. Perfect. Um, so this right here, let's do s dot. So this is our, what did we call it? We called it atomic resolution image. So we've already done this. Basically, this is what this is saying, but it's saying assign it to S. So now we have our S value is, and if you just type in S and then shift enter, basically what it does is it'll call this repre function representative of this S object, and so the bottom of every cell will do this. So if I do this, it'll only print it once. Basically, whatever the bottom line of any cell is will be shown here, as long as it's not, S is equal to S. If I have something like this, nothing will show. So a lot of times what people will do is something like this, where it's a nice representative of what this data actually is. So the first thing that a lot of people really want to do is plot their data. So if you click plot, what this will do is this will create a plot object. It'll basically plot it for you right here. You can see that this is a fake image of a bunch of different atoms, and kind of a little trippy to look at. And so this plotting right here is a nice feature. It comes with a scale right there, and it's generally an easy way to kind of visualize. It also comes with so you've got a scale bar, and then you can see what the intensity of the image is. This is what we've already kind of showed it a little bit here, is this tab completion. So let's say that we want to create a one-dimensional signal called 10. So 10 is equal to, in this case, we'll import numpy as np, and then we'll do hs.signals.signal1d, and then we can pass the data in is equal to np.arrange from 0 to 10. And so what you can see here is now I've got this signal1d object that I'm creating, and I'm giving it some data. And then if we look at 10, we can see it dimensions, it has 10. And if I plot the data, you can see that we've got this plot that goes from 0 to 10, and intensity goes from 0 to 10. So it's a pretty unremarkable signal right there. But what's nice is that if we start typing 10, we can see that Jupyter will basically autocomplete here, so we can see, okay, 10, and look at that. We can do the same thing as we did above. We can see 10 dot, we can do all of these different functions. So we can add Gaussian noise, we can calibrate it, we can crop it, take the derivative. If we take the f of t, now we get the complex signal, and you can see we can kind of we can plot them together, and so then we get this plot of the real and the imaginary part of the f of t of 10. So this is all quite easy. Another thing we can do is we can call this print summary statistics function. We can see, okay, what's the mean of the spectra, the standard deviation, min, what's the first quartile, the third quartile, medium, max, all of this good stuff. Okay, let's see what we got on the chat. Yeah, so this syntax error when running, exactly, perfect. Yeah, so when you're running, basically, A dot is just like you can think of it as moving lower in a way that things are organized. And so hs.signals, and then if I just add this is the module, so it's the module hs.signals, and then you can see where it's located actually within my computer. And then if you go in here in base signal, this is just like a class within this file signals.py. There's this class base signal that exists there. And so you basically in this case, like the dot is accessing an attribute or ability, something underneath the signals class. So we're gonna try and load a DM3 file. So one thing that's super nice is that HyperSpy uses this package called RosettaSci.io. So if you go, let's go here, and I can chat, and I can chat to. Does this go to everyone? Maybe I can't. Okay, perfect. So I think we'll go to everybody. Okay, so yeah, if you go to this page right here, this is this package called RosettaSci.io, and this is just a package for loading files. So even if you don't want to use HyperSpy, you can use this package to load all of these different file formats. So you can see, it reads things like from the Arena to the Direct Electron DE5 format, to MRC files, to MPAD files, NumPy, things from Pantarei, DM3. You can see whether or not it writes to it as well. A lot of times people will want to write into certain file formats and compare between different packages. And for a lot of people, like, this is the most useful part of HyperSpy is like being able to load your data, because ultimately that's been a barrier in the past, and so this is something that we've really tried to support. If you want to, if you have some data that you want loaded, what you can do is you can try to, you can basically add in a feature request here and say like, hey, this is some data that I want loaded into HyperSpy, and people will try and help you out. If you do this, one thing that we really need is we need a small data set that we can use to test. And usually the best way to do this is if we can get some buy-in from the company. Sometimes that's not the case, but if we can, it's a lot easier to decode a file format if some company will give us information on how to load the data. There's a lot of these file formats that have been just reverse engineered over years. So a lot of these file formats have been just reverse engineered and are, you can see here how, like, some of them are fully supported, some of them are not. So yeah, let's see if there's any. Yep. So what happens here is we're going to load this DM3 file. So if we do hs.load, and then if you put basically we're going to make a string. And so in strings in Python are denoted by these double quotation marks or a single quotation marks. It actually doesn't really matter as long as you don't mix and match them. And so here, if I start with this quotation mark, there's this tab function, and you can see basically the different, these are paths. So these are different files within my file system. So here we've got a eels silicon 15 DM3. And if I do call this hs.load, what it will do is it will load that data set. So if I call this my silicon hatf, usually what I like to do is I like to give things descriptive names, especially when you're it really helps kind of when you're down here and you've got 5 or 6 different files open and uh, you're trying to deal with all of these. So what's nice here is that this just automatically loads. You can see here it's an image that's 1040 by 1264. Don't ask me why those numbers are so weird, but I guess it's a HADF image, so it can be kind of, they can scan whatever they want. So let's take this SI HADF. Oh, so we have to, basically, I didn't actually run this, and so this is now not actually assigned to this SI HADF. So I have to rerun it, and now we've got this SI HADF object. And so if you look at it, you can basically use this dot notation, and then you can push tab, and you can see, I have to, yeah, so they just print here. They just are saying print it. So you can see that print is basically the same thing as doing this. And what we can do is we do take a lot of effort into loading the metadata. The way that we organize things is we have 2 different ways that a metadata is stored. And so usually there's, oh, sorry, this is not a, so you can see I messed up there a little bit. So this is, if you look at this SI, so this silicon HADF, and you look at the original metadata attribute, so this original metadata attribute is basically all of the metadata that we get from the file. So we basically just dump anything that we get from the file into this, and it's usually in this kind of it's like a tree-like structure, and so you can actually, there's these little carrots, and you can look at each of these individual carrots and then see the different document tags, the window position, the image group. So most of this means absolutely nothing to a lot of people, right? This is all information that that Digital Micrograph cares about, but we just include because it might be useful to somebody down the line. What's more useful is we take this same data and we just create a metadata. So if we look at SI HADF metadata, this will go through and give us information about the acquisition mode, beam current, beam energy, camera length, magnification, which microscope. We have information about when we loaded the file, basically what version of HyperSpy was used to load it, a timestamp for when it was loaded, and then if you were to save this data set in a different form, it would basically update this, and so it would be a second thing here. So it's a really good way of tracking, basically, where we know that this came from a DM3 file. We know when it was first loaded, in addition to everything like the date that it was collected and the original file name, everything like that. And then we can change things like the metadata. So sometimes it does happen that you basically have some metadata here that's wrong, and so you might say that the convergence angle wasn't actually 30, or it wasn't actually 100 there. It was so if we want the camera length, so the convergence angle is what we want to add so let's say we want to add the convergence length. So what we can do is we can do metadata.tm, metadata. Sometimes you have to go back and see acquisition instrument. So you can see this attribute error. It says metadata doesn't have this TM attribute. So we want the acquisition instrument .tm, and then what we can say is we want to set the convergence angle is equal to 30. And so then if we look at our metadata now, you can see that now under this TEM, there's a convergence angle, and our convergence angle has been set to 30. So this is a nice way just to make sure that all of the metadata stays in there. If you wanted to do, 30 milliradians, you can also do that, and then it will show up as and that will show up as 30 milliradians. So then that's nice just to so that you have this. What's important is like this hasn't written back to this original DM3 file. We'd have to change that within the so it hasn't written it back. So what's important is that like this doesn't actually change that file. I'll show you later how to actually save the data set. So you might be able to basically save and then go back to it. The other thing that you might be interested in is things like the axes. So if we do this same silicon HDF and then we type in axes manager, you can see we've got a signal name. So we've got X, Y. These are the size of these two axes. So we can see we have X, Y. We can look at the offset here. So basically this is starting at 0. The scale here is 0.0. So basically every pixel is 0.003 basically nanometers. So pretty small step size there as well. So if we and then we can do the same thing here where we get the first axes. So if we do axes manager and it at 0, we can see this is the x-axis. We can also do silicon HDF axes manager at So in this case I jumped slightly ahead. Sorry, let's go back here. So now let's try this because this is also. So let's say we have, I'm going to press A again, and we're basically going to add in a new file. So now we can do silicon. So this is our silicon. I think this ends up being in. Yeah. So silicon eals is equal to hs.load. And then let's load the second file here. And so there's a full range corrected DM3. What's annoying sometimes about these is that, so let's see what happens here. So right now you can see it says no file name matches this pattern. The problem is that this file name has some spaces in it. And so these escape characters right here. So Jupyter just doesn't quite, when it loads the files, sometimes it doesn't know what to do with spaces and things like parentheses. And so when it auto completes, it completes it wrong, which is a little frustrating sometimes. But what you can do is you can just delete those escape characters, and then it should load right there. So now we've got this silicon eals. What we can see now is we've got basically we've got an eals spectrum. So this is no longer a signal 1D or a signal 2D. This is a specific eals spectrum signal. We have dimensions of basically it's 65 plus 75 in the x direction, and then we have 1,340 channels. And if we actually look at this axes manager, we can see that we have X, Y, and then an energy loss channel. And so what we were trying to show here is that rather than indexing like this, we can also index like this and say, okay, give me the energy loss spectrum. And that will give us the basically the offset and the scale. Gives us the ability to give us things like dot scale. This will give us the scale. This will give us the offset, units, everything like that. And we can also do this, and we can set them to. So in this case, I didn't finish my string, so we're going to do that. We can set them. And then what that will do is now this is no longer in electron volts, it's in volts. We can also set this back to, so now it's in electron volts. You can see how that kind of changes it. So a lot of times, like if your units or stuff are wrong and you want to adjust them, then you can just do that there. Yep, so that's the same thing that this is doing right here, is just getting the units. I think we should do that on that scale. Okay, so this would be the question of whether or not I've broken this on my development. So what you can do is you can also use these GUIs. Some of these, like I kind of, the way that HyperSpy was designed was with this idea that a lot of people were going to be coming from using things like digital micrograph or other GUI type softwares, and some of these programming type things are it's kind of tedious to do sometimes. And so what they wanted to do is create this sorry. So there's a bunch of these axes managers that GUI, and it's going to yeah, crap. So we're gonna maybe skip this just because, so basically, if you want to try this, you can look at the just for like the sake of time also. So basically what this uses is to use these packages called IPy widgets and then traits UI. And what this does is it makes a it will basically take and give you like a loaded GUI to adjust the offset and the index and the size and whatnot here. But for the reason why I tend not to use them is basically because what's nice here is that you can see exactly where the Jupyter Notebooks becomes another way of kind of documenting what you're doing. So if I say here my units are equal to volts, next time when I load up this same notebook, then if I run through all of these cells, basically I go through and run all of these cells, it will automatically go through and then run all the things that matter. And so it's a very reproducible environment. Whereas that if you do something in one of these GUIs, then it's not saved, so your state's not saved, so you can't immediately go back in and run it all the way through. Yeah, so what's wrong with at least my installation is I'm running this development environment, and then sometimes getting these traits and these IPy widgets packages to work sometimes becomes a bit of a pain. But for the most part, it's they tend to be more of a crutch than anything else. But what is important is kind of the interactive visualizations. So let's say we plot this. Okay, so you can see now everything is way too big. So I'm going to zoom out. So if we plot the EEL spectrum, let's plot things. So usually what is done in Jupyter Notebooks is what matplotlib inline. So it's inline plotting. So most of the times what you'd see is this. You'd see basically this is a XY EL silicon. So this is in real space XY. This is your energy. We're basically getting the spectrum from the position 0, 0 right here. And this is all static. What you can do is you can use this IPy matplotlib package. So if you do matplotlib, IPy matplotlib, what this will do is this will make these plots dynamic. And so you can see up in the top right hand corner here, we've got this little red square. So if you click on that, you can kind of drag it around and you can see how the spectrum changed. So we can go here, we can see how things are kind of changing. If you have a huge image, so this is what happens a lot of times with 40 STEM data sets, you can hold down Shift and then click, and then that will jump to a different position. So you can see we kind of jump around the data set, and we don't have to drag through all of the other data. This becomes really important if your data set is huge. So if you have a 100 gigabyte size data set, if I want to drag from this position over to here, it might take, it might end up taking a long time to actually process all of that data right there. You can also kind of resize these and then use, use these tools to kind of like zoom in and whatnot. So this is something that's really important. Is something that we think is really important, is to be able to kind of visualize this data set. Let's see if there's. So if I press E, what you can see is now we have a second pointer. So you can see that we have a second spectrum. So this works only for kind of one-dimensional data sets, but you can kind of see that if we drag each of these individually, then we can see these two plots overlaid. If you want to, sometimes these pointers end up being really small. So if you click Shift and then plus, it'll make them bigger. So then they're easier to drag around. It doesn't integrate over that area. That's something that I've been really trying to make work, but I just haven't quite gotten there to make that so smooth and effective. If you have a, you can also use the arrow keys to move them around. If you have a Mac, this usually ends up being I think it ends up being Shift and then the arrow keys. Otherwise, it's Command, I think, in the arrow keys. This is all set in the preferences, and maybe I can send something out later about how to exactly do this, because this is sometimes something that people get stuck on. But yeah, you can just use if you hold it down Shift and then use the arrow keys, things will move around on a Mac, and then I think it's Control or Command on a Windows computer. It's also within the documentation. Yeah, so I mean, I think this there's a couple of these things that only work. For example, a contrast only works in the matplotlib Qt backend. So another thing you could try is you can use and if you change this from matplotlib, apply matplotlib to Qt, this will instead pop out the plots. So now that they're not within the notebook. This is another thing where I'm not super, a lot of what's great about these notebooks is that things are embedded, right? So like I come back in 2 days, I can see where I left off, and I can see where I left off these plots. Whereas if you pop these out and make them and use Qt, then that state gets lost when the notebook gets saved. So let's see what our how to select multiple pointers. So I mean, these pointers, like how to click onto them, or I mean, like for these multiple pointers right here, you just kind of click in the middle of them. What made the extra one is E. If you just click on, you have to click on this plot first, and then you click E. Okay, so then he's talking about customizing the plot. Yeah, so so in general, this is a good point to come. Maybe this is something we can talk a little bit more about later in a different session, is how to make really nice plots. Basically, these plots are really supposed to be for just for visualization. Part of the problem is that, like, adjusting these plots becomes a little tedious, just because there's a lot of background stuff to making these interactive, and so there's lots of additional components involved. So what we do have is we have this hs.plot function, hs.plot, and you can think like you can do things like this, where in this case, basically what you can do here is you can plot multiple spectra, and you can adjust. This function has the ability to, let's maybe show what this looks like. So you probably won't understand exactly what I'm doing right here, just because this may be slightly more advanced. But what we're getting here is we're getting the position 0, 0, and then let's compare it to 10, 10. So this is just the pixel position, and these are going to be 2 spectra, and we can plot those spectra, and you can see now they're overlaid. If you want to, we can add color, and we can say, okay, red, green, and then you can see how we've changed those two colors. So now we've got red overlaid with green. You can do so many other things here, like you can change the style, so if you want style is equal to, you can see cascade. So now they're on top of each other. So there's a lot that you can do with these types of functions. But generally, this is a little bit better for creating these static plots, rather than using anything like this interactive plot. This interactive plot, just there's some limitations to it. So we can maybe cover that in like a later session, just because you can spend an hour talking about how to make good plots. Yeah, so okay, and then there's a question about how to deconvolve the spectrum. Yeah, so that's something that we can cover maybe in a later session. If you want some support on doing that, if you want to kind of go ahead of the group, let's see, GitHub. So this data analysis, perfect. You can see there's things like curve fitting right down there, or EDS and EELS. And this will go through all of the things on how to quantify fine structure elemental mapping. So yeah, these are kind of just like basics that are good to start with. And then something that might happen a lot is that if you have more than 20 figures, this might start to get slow depending on your computer. And so matplotlib usually says, so all these plots are made using matplotlib, but matplotlib will say, okay, you need to close some figures. So what you can do here is you can do import matplotlib.pyplot as plt, plt.close all. And basically what that does is it closes all these figures. And so they're no longer active. So you can see I can no longer drag any of these things. Another thing you might want to do is take this EELS spectrum, so EELS silicon EELS data, and then we can use this 2 signals, this function right now, and what you can see here is that things have flipped. And so now we have a signal 2D. You can see that our one dimension, our energy channel is flipped from the image dimensions. It's right here. So our real space dimensions. So now we have a spectrum. Yeah, so that would be our spectrum image. And if we were to plot that, you can see now, if I use shift and then you can see kind of as we go across, we can look at each of these individual, basically each of these peaks, and you can see the different structure in there. So you kind of start to see some of the atoms within this data set. And it's basically the transpose. Yeah, so that's just what's showing what this is, and that's what this plot function basically is showing the energy spectrum. We can also do the same thing here with the transpose function. So if we use this .t, spectrum image .t, we can see now that we've got this. Oh, sorry, this is the spectrum image. If we take the silicon eels and do this .t, it's basically the same. And you can see we can plot this. So we can kind of chain this together, make this and plot this same as before. So now we can see our different channels. Okay, so we're going along. We've got a couple of minutes. We've probably got, let's go for like 9-10 more minutes, and then we can stop for some questions. Other thing you can do is, let's say you want to save this. You want to save this spectrum image. So we've got this spectrum image. We can have there's a save function, and so usually what I recommend people is save this in. We've got this HSPY file format. This is kind of the only file format where you will always save all of your metadata. So silicon spectrum. Basically what this will do is this will save, and then we can do hs.load our spectrum image later, and basically you've got your And so usually what I tend to do is like make sure that, when I'm working with a data set, I like to load it in, and then usually I'll end up resaving it along with some metadata and other things that I like to add to it, make sure that all of the units and stuff are correct. But yeah, you can see how here we've resaved this, and and you can do, if you want to, you can, I can't remember if this works or not. Yeah, so you can see in this case, it doesn't support writing to something like a DM3 file format, but we can try to do something. In this case, our spectrum image is a series of images, so I think we can save it something like an MRC. Yeah. So you might have to try, and I think a TIFF stack will work. Okay, yeah. So you can save it as a TIFF stack. There are different, but what's important is that now this TIFF stack doesn't have any of the associated metadata. So if we did hs.load our silicon spectrum image.tiff, so it doesn't really have any of the same metadata that we really wanted from before, which is here. So it doesn't have things like the TEM acquisition, all of that information about the detector and whatnot. So that's just an important thing to remember. Certain file formats have certain metadata that they do allow, and you might need to play around with it a little bit. Yeah, save it as a TIFF file, load it, plot it, exactly. Let's see. So then let's talk about indexing, because this is probably a good place to stop. Let's say we hs.load, we're going to load this astronaut file, and usually this is going to be our image is equal to that. We can see here it's basically 3 channels, and then it's 512 by 512. Usually the first thing that I do is I plot anything. So I usually will just immediately plot it. What we have here is we have this astronaut. And you can see these are actually the red, blue, green, and blue channels for this astronaut photo. What we can do is, like we talked about before, we can use this plot images, hs.plot images, and we can actually just plot images are, what this will do is this will plot the 3 channels side by side using this plot images functions. You can see there's a lot of, this is like the image equivalent of this plot spectra. So you can see there's lots of different things that we can add there. So for example, if we want to click a label, you can do red, green, blue. So now you can see that this image has nice red, green, blue. This function will also return the, if you can see, these are all of the different parameters. It will return an axes list. So you can also do this import. So we've already imported this. So plt.figure. Yeah, usually what I do is this. So plt. We can pass in this figure using this fig is equal to f. And color bar onto a different figure with 2 axes. So I might have. It's not. Come on. I think it's because it's still active. So yeah. This is always the fun part of live coding anything. plt.figure, and then adding color bar on a different figure with 2 axes, then figure this color bar, figure color is on. It's weird that doesn't. Because this figure, I guess I should look at the documentation, but I'll send out maybe afterwards. I'll send out the right syntax for that, because that is a question that we had, was how to make those plots. yeah, we can see if that will work. And then fig f, and then, yeah, perfect. That makes it a little weird that we've got this subplot because it's actually plotting it within the subplot. Because this actually should be, I mean, so actually subplot 3 and then yeah, okay. So that's actually the right way. Thank you. Yeah. So what you can do here is you can do something like this, where you can give it basically the axes and the figure right there, and then create a. So then what's nice here is then you can do f.save fig, and then you could save it usually as so my figure. So then usually what I like to do is I like to save it as a as like an SVG. What's nice is that if you have, basically this is like a standard vector graphics image. And so what's nice then is that you can open and you can edit these files later. And so this, I tend to use things like I like this program called Inkscape. What's super nice is we can just open up. So if we do open, and then we'll go to the top level, and then we'll have to go through to G. You can see I'm getting started. So now you can see this figure is now open in Inkscape, and so what's nice here is that you can, let's say you're like, oh, I really wish that this part was higher, so then you can change and adjust things, and this is something that's super nice. Obviously you don't want to like change, and you can really edit things like that, so you really just want to make sure that you're not changing things too much. But this is a nice hack to be able to like, okay, I want to take this and then take this, all of these images and then put them on a nice like composite figure. And it's really nice that Matplotlib offers that as an option to do that. So we got like 8 minutes left, so I can maybe get some questions. Maybe show one more thing in like 2 minutes, and then what we can also do here is use these iNav signals. So let's say we do our, let's say we take our image, image.inav, and we just go, this is just the first channel. You can see that if we were to plot it, we would just plot the first channel. That's nice. We can also do it with the isig function. So isig, we can go from 0 to 100, 0 to 100, and this will basically, this isig, this will basically only give us the top right-hand corner of the left-hand corner of the image. We can also chain them together. So in this case, we don't really want this navigator. So inav at 0, that isig, you can see we've just gotten that top portion of the image. So it's very much similar to, like, if you ever used NumPy, it's very much the similar indexing. What's different is that we've split things into these navigation and these signal. So this is a navigation and signal dimensions. And so you kind of operate each of these individually. If you use decimal places, it will use the actual units as well. So in this case, this image, our axis manager, you can see our, so we do have a scale. So our scale right now is 0.13. So if, let's say we would go to 0 to So if we went from 0 to 10.3, now you can see this is basically actually using the real units. It's using the centimeters. I think even like we can do this. And it will change the units. Although in most cases I don't. Yeah, so in that case it's actually using meters instead of centimeters. So you can, this is a nice way to kind of activate and to use it. So if you want to, you can go through the rest of this getting started notebook kind of by yourself. There's some things that we might want to cover a little bit more in detail next time. So for example, we will talk about this map function a bit, but for most of this stuff, it's stuff that you can kind of, if you go through it a little bit, you'll get the idea. Hopefully this is a good starting point for people, and maybe we'll send out a poll and see what people are interested in, and then go from there the next time. So let's see if we've got any questions. Please, if you want to unmute as well and then ask a question, you can. I also, I can stay around a little bit longer and do that as well.
There is a question in the Q&A. I'm not sure if you have seen it. Is there a way to isolate elements in EOS with HyperSpy, for example, color map for each element?
Yeah, so if you want, let's see if we have an example ready. So let's say if we did eels. So let's say we go to this eels and we go to the so this tutorial right here, this eels mapping, basically this is looking at a copper zinc. And so, this is kind of the, let's scroll through this and then see what it, let's just run it all and see what it gives us. It's been a little while since I've gone through this exact notebook, but what I'm doing here is I click this fast forward button. This basically just says restart the kernel, and then basically restart this notebook, and then go through and run all of the individual cells. Usually, actually, what I recommend for people to do is there's this saying with the people who use Jupyter Notebooks a lot that a notebook is not complete until you have clicked this restart button and then restarted the kernel and then run all of the cells. And because if it doesn't run all the way through, then it's not really it's not a super valid notebook. You can see up here. And okay, so now we've finished. I have a lot of plots that aren't showing up. Okay, so this is doing a lot of fitting. And this is basically what that, so this is what this is showing. It's basically, you've got this zinc L3, and then we've got this copper L3 line. What it's saying is it's plotting these side by side, and then you can also do this plot images and you can overlay them. And so in this case, it's overlaying the zinc and the copper, creating this overlaid image right here. So, I mean, this is something where, if this is something that people are interested in, we can go over this maybe in a separate session. But also this is freely available. So if you want to, you can go through this. So if you go to the hyperspy.org, there are also some examples here, fitting ES lines, EELS curve fitting. So these examples are a great place to start too. So this is basically fitting a EELS spectrum, and it's very similar to kind of, this is maybe slightly less involved than the example, but it's a good like, this is just a pretty easy example of how to do this quickly. And so basically that's what these examples are meant to do. Uh, these examples are kind of meant to be like, you know, 2 minute introductions on how to do one specific thing. Whereas like the tutorials, things like these tutorials are going to be more in depth, like elemental mapping or something like that. So there's lots of, I mean, there's lots of these tutorials out and about, and you should just be able to kind of run through them as you can. Yeah, so typography. This is one thing where, to be honest, so as somebody who manages the Bixum, which is does a lot of like the typography stuff. I never really ended up doing any typography in my PhD, and you know, a lot of the other people who've been managing and like developing Pixum haven't really done much typography. As a result, like this is not something that we're have any real expertise in, and so it becomes a bit of a challenge to kind of write that code, and nobody really wants, you know, somebody who's not an expert in it. So what I would recommend is, so there's a couple of different packages out there for doing kind of this for doing typographic reconstructions. The one that's kind of maybe the newest, but I think they've had really good results, and they're still kind of working through you know, how to develop this, is this package called QuantDM. And so within QuantDM, there's you know, diffraction, and so that's in. They have a bunch of typography models. What's really nice about these are all done using this package called PyTorch. So it's quite fast, and so especially if you have, you know, typography is something that really benefits from having a GPU available to you, and so these are all run either, you know, you can either run it on a CPU or a GPU, and there's lots of these, like, you know, iterative methods and kind of generic methods and stuff like that. So that would be my suggestion. There's a lot of other, you know, so the other thing, this is kind of meant to be the next step from Pi40 STEM, and so this is being developed majority out of Stanford, but with a lot of contributions from people elsewhere. So maybe this is something I would look at, you know, but it's also a very young project, and so it's, you know, keep that in mind. There's also a lot of packages from, like, I think David Muller's group has some scripts for that as well. So yeah, TypeRad, yeah. So this is another one. So there's quite a few different typography, different focused packages. It's, yeah, and this one was also powered by PyTorch. Yeah, this is also another really nice one. So it's something that if we want to, it would be good to, if we wanted to like have that as an option for, you know, having somebody come and speak, that would be another great option, but that is not something that I would feel super comfortable talking about. Do you have any other questions?
Is there any other questions? Feel free to type in the chat.
Yeah, or you can unmute and ask too if you'd like. You know, it's a little more frightening, but
Or if not, we'll close out this webinar. Thank you so much, Carter, for this very nice tutorial. So after the webinar, we'll send out a poll, like a post-webinar survey, basically asking like our interest, like what's other topics you want we want to look at in the future sessions. So but for this nice introductive tutorial, I hope everyone can get good takeaways and get started with using Python and get adapted to the like the coding environment. And also, if you have further questions, feel free to send us your questions. So I'll make sure I forward to the correct person. I'll forward to Carter.
Yeah,
So
and if you want to, you can also send out my, I don't know if they have my email address, but if you want to, you can always send me questions on my email. It's at least part of my job is for Direct Electron is kind of interacting with the community, and this is something I enjoy doing. So I might not always be the fastest to respond, but I will eventually.
yeah. So thank you so much. And yeah, well, this whole webinar is recorded. So later we'll post the video on the GLMS. So our website, Great Lakes Microscopy, Great Lakes .microscopy.org. So please check back later. We'll please give myself some time to process, and we'll make sure upload the video as soon as we can. And yeah, please make sure you answer the post survey so that we can schedule other future series and tutorials on interesting topics. So thank you, Carter. Thank you, everybody, and hope you enjoy your rest of day and have a good weekend.
Thanks.